In the C Supreme window, you have different tabs. On the left-hand side, you have all the files that are included in the project. On the right, in the middle, you have the main input file, which is a template that was generated by the mask editor program. And as you move the cursor from line to line, you'll see on the right-hand side, the helps wizard is updated. This allows you to see a description of what each command does, as well as the various parameters that are available for each command. So the first command you see is a mode command. This determines how the solver works in C Supreme. By default, you have a 2D simulation which is available, which means one mesh plane, a quasi 3D, which means multiple mesh planes, but there's no diffusion between the mesh planes. This is good when you don't expect any diffusion to occur in the Z direction. And it saves a lot on the computation time and the memory requirements. There's also a full 3D mode that's available if you want to spend the computing resources to get a more accurate solution. So here, by default, Mask Editor gives you a quasi 3D setup, which is sufficient. The 3D mesh command is what instructs the C Supreme to load geofiles, which have been generated by Mask Editor to represent the mesh generation commands in the various layers. The init command sets up the initial state of the substrate. So here we have to add a few things. First of all, we have to tell the software what's the initial doping of the substrate. So here we want a p-type substrate with a boron concentration of 5e17. And we also specify the orientation of the crystal. After the initial setup, the Mask Editor program has included a few things for us. So the first thing it's included is the STI mask. And this includes a file, which the MSK extension. And if we look at the details of that, you'll see several C Supreme commands which define the etch profile and also the change material operation. After that, if we check the second mask it's added, you'll see there are a few commands that have been added before the operation of the mask, just like we specified in Mask Editor earlier. Since Mask Editor doesn't support all the options of the diffuse statement, we're going to fix it here and add a dry O2 parameter, and this tells the software that we're going to grow a dry oxide layer. After our diffusion, we deposit the polysilicon, and we note that originally we specified the mesh inside the substrate. Since we're having extra layers on top of the substrate, we specified the mesh layer command, and this defines additional horizontal mesh lines for the new layer. After that, we actually have our mask, which is for the second step, which is included. And if we view it, we'll see the etch commands, which remove the oxide. For a final mask, we note that the mask comes first because that's what depositing the photoresist. After that, we do the implantation for the lightly doped channel, and then we etch the photoresist before using a diffusion to activate it. After that, we deposit nitrides, but we're going to modify it a little bit in order to improve the quality of the surface that's generated. We're going to use a space parameter to add some additional mesh points. And this allows it to give a better approximation of the rounded edge that's created during the deposition. After that, we etch the nitride, and then we do the final implantation for the source and drain using arsenic, a final diffusion time, and then we do a regrid step to refine the mesh near the PN junctions. Before we do the simulation run, we have to specify the output. And we note that Mask Editor already generated some struct commands, and these output the structure during the process simulation after every major step. At the end, though, we want to do an export command, and this is what is going to generate the mesh that the device simulator can use. So in order to run the simulation, we just click the Start button here and specify our main input file. You note that as you run, the command that's being run will be highlighted. This is going to take a few minutes. Okay, so now it's doing the final export to the APSIS mesh, and we have the finished simulation at the bottom, which tells us everything is ready. So we can go to the output file section to view our structure. So we're going to take the last one, which is the after the implantation mask has been used. And at first, the Crosslight View program will show you the structure of the device. And then we can plot various variables. So if we go to the right and select net doping, then we have a nice view of the doping profile in our device. So in the Crosslight View program, you have different options. You can rotate the structure to get a better view. You can define a 1D or 2D cut at a specific direction. So if we view the result on the first mesh plane, we get a better view of what the structure looks like. To do the final device simulation, we have to go back to SimUSys Supreme and use the contact designer. So we first start by opening a file that's been generated for us during the export procedure, and then we're going to create 3 different contacts. Each contact is distinguished by its number. And so the contact number 1 is going to be source contact, and we're going to define a specific X range where it exists and a Y range also. So the Y range is a little bit tricky because in Supreme and APSIS, the Y axis is in the different direction. This is a matter of historical convention. The second contact is going to be the gate contact. And the third contact is for the drain. An important thing to note is that contacts for APSIS are not actually metals that you would see in the Supreme simulation. They're equipotential boundary regions, and they don't specifically have a material assigned to them. So after doing the contact definition, we now save and generate a new input file, which is going to be used in the APSIS simulation. And this file is going to be loaded into our template for APSIS. So now we can go back to our main launch window and go to SimUAPSIS. And we're going to open up the template that was been generated during the Supreme export procedure. So the file that we need is main3d.sol. The other files have been generated by the various tools during our initial procedure. Material 3D has been generated during the initial export and defines the different materials. Contact 3D is part of the contact designer that we worked on before. Main 3D is our main input file for APSIS.